Hello, everyone. Today, we're diving into a critical topic for any growing application: scaling message queues using Apache Kafka. In the world of high-traffic systems, handling millions of events per second isn't just a luxury, it's a necessity. Think about a major social network or an e-commerce platform during a flash sale. Every user action, every data update generates a flurry of messages that need to be processed reliably and efficiently. Traditional message queues often hit their limits here, struggling with both throughput and data integrity. That's where Kafka shines, offering a robust, distributed solution that can handle immense scale. By the end of this lesson, you won't just understand Kafka, you'll have a clear roadmap for implementing it in a production environment. You'll learn how to design a Kafka cluster for parallel processing, ensure that every message is handled exactly once, and integrate Kafka into a real-time system. Our goal is to equip you with the knowledge to build highly scalable, resilient messaging systems that can stand up to the demands of modern applications. Let's get started. Imagine a system like a large social network. When a user posts an update, it's not just one event. That single action can trigger a cascade of downstream processes, updating timelines for thousands of followers, sending notifications, calculating trending topics, and even feeding recommendation engines. This creates an enormous volume of messages that traditional message queues often struggle to manage. For instance, a simple Redis pub submodel is fantastic for quick and ephemeral communication, but lacks the durability and partitioning needed for persistent, high-volume data streams. If Redis goes down, your messages are gone. RabbitMQ, while offering excellent reliability and message guarantees, can hit bottlenecks when trying to scale horizontally to truly massive throughputs. It's great for smaller, critical workloads, but less ideal for the sheer volume we're discussing. This is precisely where Apache Kafka steps in, providing a distributed, fault-tolerant, and highly scalable solution. It's designed from the ground up to handle millions of messages per second by distributing the load and persisting data reliably. Let's break down how Kafka achieves this incredible scale. At its heart, Kafka is built on a few core concepts. First, partitioning. Think of a Kafka topic, which is essentially a category or feed name, as a large conveyor belt. To speed things up, Kafka splits this conveyor belt into multiple independent partitions. Each partition handles a subset of messages, much like having multiple checkout lanes at a busy grocery store. Messages within a single partition are always ordered, but overall processing is parallel. Producers, the applications sending messages, use partition keys, often a user ID, to ensure related messages always go to the same partition. This maintains order for user-specific events while distributing the load evenly across all partitions. For consumption, Kafka uses consumer groups. Multiple consumer instances can form a group, and Kafka ensures that each partition is consumed by exactly one member of that group. If you need more processing power, simply add more consumers to the group, and Kafka automatically rebalances the workload. Finally, Kafka provides exactly once semantics. This is crucial for data integrity. Through idempotent producers and transactional consumers, Kafka ensures that even if a message is retried, it's processed only a single time, preventing duplicates and ensuring your data remains consistent. Now, let's put these concepts into practice and design a production-ready Kafka architecture using our social network example. Our Kafka cluster would typically consist of 3 Kafka brokers with a replication factor of 3. This ensures fault tolerance. If one broker fails, your data is still safe and accessible. Topics would be partitioned by a hash of the user ID, distributing the load while maintaining the order of events for each specific user. The message flow starts when a user posts a tweet from the front end. This goes through a Node.js API, which then acts as a Kafka producer, sending the tweet to our tweets topic. A fan-out consumer service reads these tweets, calculates who needs to see it, and then produces timeline update messages to another topic. Subsequently, a timeline consumer picks up these updates, refreshing our Redis cache and pushing real-time notifications to connected users via WebSockets. Crucially, we also incorporate a dead letter queue, or DLQ. This is where messages go if they repeatedly fail processing after several retries. This mechanism prevents a single bad message from blocking the entire pipeline. For exactly once delivery, we use idempotent producers that are safe to retry, transactional consumers that process messages atomically, and consumer-side deduplication logic to catch any lingering duplicates. This layered approach ensures robust data integrity throughout your system. Kafka isn't just theory, it's the backbone of some of the world's largest companies. For instance, LinkedIn created Kafka to handle their massive activity stream processing, allowing them to process billions of user interactions without data loss. Their key insight was the need for a system that could handle both high throughput and reliable persistence. Netflix processes over 700 billion events daily through Kafka, from user interactions to video streaming telemetry. They partition not just by user, but also by geographic region to reduce latency and improve user experience globally. Uber uses Kafka to route ride requests, location updates, and driver matching. By partitioning by city, they ensure local processing efficiency while maintaining global coordination. Our Kafka implementation also seamlessly integrates with concepts from previous lessons, particularly distributed caching. Kafka messages can trigger Redis cache updates, ensuring consistency. Background consumers can pre-populate caches, known as cache warming, and Kafka's message ordering guarantees that cache updates happen in the correct sequence. You've learned how to design, implement, and understand the critical role Kafka plays in building scalable, real-time systems. To test your understanding, consider how would you adapt this Kafka architecture to handle a sudden, massive surge in message volume, say 10 times the expected peak?